Hey guys, Miss McCorn here. So go ahead and take out your handy dandy notebook and take a few notes on 5.3. This is how the change in concentration over time is going to affect the chemical reaction rate. So we're going to look at the rate law of a chemical reaction using data, and we're actually going to look at some graphs today, so that's going to be pretty interesting. So the first thing I want y'all to remember is that when we have a zeroth order reaction, the rate is actually equal to K, the rate constant. And that is because that changing the concentration of whatever it is of that reactant has absolutely no effect on the reaction rate. So that means that when we look at a graph of, when we're looking at a graph of the reaction rate, when we look at the concentration of the substance over time, we're going to have a linear reaction here. A linear rate here. So our slope is going to be exactly the same no matter where we are. So that is very different from a first or second order rate. So when you look at this, any time that you are looking at the rate versus the time on a graph, your rate would always be constant. And if you ever looked at this in a little table like this, I really liked this slide, which is why I want to show it to you. No matter what the concentration is of your reactant, your rate is always going to be exactly the same. In this particular case, 2.0 times 10 to the negative third molarity per second. It's not going to change. It's going to disappear at the same rate over time. And this is a particular instance where that does happen. So this is what your equation would look like. You actually will be given this equation here on the AP exam. You will not be told that this is only used for a zeroth order equation, or zeroth order reaction, but you will be given this actual equation. So what you see here is your initial, your final and your initial concentration. So this, of course, here is your change in concentration is equal to the inverse or the negative of your constant times time. So that is an important equation that you'll need to kind of have an idea of or kind of keep it in your mind, but it is not necessarily something you need to memorize. Just knowing that this goes with a zeroth order equation is definitely enough. So we can also see this if we wanted to look at it graphically, that your M or your slope here is going to be the same as your rate constant, your K, and then your B or your y-intercept is going to be your initial time. So that's your y equals mx plus b, or your slope line that you usually use in algebra. It kind of can look like this. So if it's a zeroth order, you would get a straight line out of this. Anything else, if you're looking at something, and we'll look at this in a moment just to show you, though, if you're looking at something that is a first order or anything else, it's not going to be a straight line. The only one that is going to give you a straight line is going to be the zeroth order. Anything else is going to give you something, that's curved. So if we are looking at a first order reaction, we know that the rate is going to be K times the concentration. We know here that every time we have this, we are going to double our rate. So when we see this, this is going to be our graph of our reaction rate. But then if we go through some calculus, and I will show you the actual reaction, the rate law equation in a moment, but this is what it would look like graphically. You would have this linear when you do the rate, or this would be the natural log of the concentration, and you graph it with the time, you would get this nice linear line only for first order reactions. So here what you see is our concentration of this is peroxide, for example, and our time here. And you would have this linear line on this side here, which is, again, natural log of the rate and the time. We aren't going to do a whole lot of in-depth examples on this. I just want to give you an idea of what this would look like. So this is what your equation would look like. You'd have the natural log of your concentration at any given time, subtract the natural log of the concentration at initially, and that is going to equal to the negative k times t. And so again, you can rearrange that to where it can be that y equals mx plus b, and you're going to get that linear line, which is really interesting. So again, we are going to focus a little bit more on something else you'll see in just a moment. But so what I want to focus on mostly is the rate constant and how it is related to half-life. So this is really the most interesting thing, and is really important when we talk about the radioactive decay of different substances. So the half-life of a reactant is the time it takes for half of the available molecules to convert or change into the product. So these are all going to be first order rates, first order reactions. So there's only one reaction in a first order reaction. There's only one reactant that affects the rate. One of them should be probably a 1, and the other one would be a 0. So that one is not going to affect the concentration at all. Or it might be that it's a decomposition reaction where there's only one actual reactant doing anything at all. A lot of times when we're talking about the radioactive decay, we're talking about those decomposition reactions, and this is what is happening. So what you see here, and what I wanted to point out, is that you have these boxes here. So what this is showing you is that here's our 100%, and after half of it is decayed, this is one half-life here. Half of it has turned into something else. And this is happening, you'll notice that nice little curve there, that is our half-life curve. So this is something that they will give you on the AP exam. This you need to make sure, I think there's supposed to be a 2 right here. It's supposed to say D 1/2 there is equal to 0.69 over K. So that is your half-life and how it's related to your rate constant. So whatever your K is, the half-life of your substance is going to be equal to 0.693 divided by K. So just to give you an idea, this is what a 0th order and a 2nd order reaction, like a half-life type graph, might look like. For a 0th order, you'll notice the half-life gets smaller and smaller and smaller as we go. The first one is really big, and then it gets smaller and smaller. And then for a 2nd order reaction, the very first, it happens very quickly, and then everything else takes a longer and longer time. Most of these practice problems we will be doing in class. I just wanted to give you a basic overview of what we're going to be talking about. You need to have these things in mind and get kind of a basic overview. If you need a little bit more information, if you're feeling a little bit confused, you can go watch the Bozeman rate constant video if you just YouTube on Bozeman Science. If a lot of people are confused, I do not mind putting a link up to that on Google Classroom. It might help you get a little extra information. Not required though. All right, guys, I will see you guys tomorrow. I hope you have a great day.